right? So exponential equations, what we'll talk about here is an equation where the unknown trying to solve for a missing exponent. Now, get a big picture of this idea. Okay? A lot of times to find a missing exponent or an unknown exponent, that's why somebody came up with logarithms. Logarithms are to help me solve for exponents, okay? To help me find unknown exponents. Okay? So somebody a long time ago came up with these logarithm tables that you had to use. You didn't have a calculator way back then. Okay? So you have these log tables. Somebody kind of came up with this idea to find, or with a logarithm to discover exponents. In anything where you have a missing exponent. Okay? So you have a lot of formulas. You have compound interest, continuously compounding interest. You have, I'm sure like some of you like in chemistry and chemistry 2, you've done like half-life. Okay? So usually in the chemistry problems, they're easier ones and you don't really need the logs. Okay? But in the more complicated ones you do. Right? So I mean, anytime you have a problem where you're trying to find an exponent that you don't know, chances are you're probably going to have to use a logarithm. Now, we're going to look at a few problems first, though, that you really don't need a logarithm to do. Okay, so we're going to start off with, I call them the easy ones, okay? And this is like number 3 there on your sheet, okay? So the easy ones, or the easy way, is to do this. You write both sides with a common base. So you want your base to be the same. So my bases in these problems would be the 5 and the 125. Okay. Notice that the variable x is what kind of number? Yes, an exponent. Okay. So we're looking for an unknown exponent. Now this one's like really, really easy. I mean, you could just, yeah, you know the answer is just 3. You know 5 to the 3rd power is 125. Okay. But let's look at this idea. And this idea doesn't always work. They're not always easy like this. Okay? But the idea there is I take both sides and I write them with a common base. So how can I write 125 with a base of 5? 5 to the 3rd power. Okay? So what happens is if the bases are the same, then what has to happen to the exponent? They have to be the same. If the bases are the same, then the exponents have to be the same. So that means that x would just be equal to 3. If the bases are the same, then these exponents. Okay? Now, one problem with this, all right? Let's just pretend just a minute. What if this was 124 instead? Could you write 124 with a base of 5? No. Okay? So writing them with a common base is the easy way, but you can't always do them that way. Now let's do a couple more that are easy like that. Alright, look at number 7. Okay? This one's a little bit tougher, but it's still an easy problem. Alright? So what I'm going to try to do here is write, again, both sides with a common base. Okay, so we've got 4 over here. Let's raise to that unknown power. Is there a way I can write 64 with a base of 4? Yeah. And what? 4 to the 3rd power? Okay. And even if I couldn't maybe come up with 4 to the 3rd power, you could also write both of these with a base of 2. Okay. 4 is what? 2 squared. And I think 64 is like 2 to the 6. You could do it that way too. If you couldn't use 4, you could use 2. All right, well, let's use 4 because it would be much easier. So, got that as a base of 4, so we're going to write that as 4 to the 3rd power. Now, so there again, if if my bases are the same, then exponents are the same. So 2x, right, set the exponents. 2x minus 1 equals 3. Okay, now it's nothing there. So we get 2x is 4. So x will be 2. Okay, no big deal. Alright, let's look at number 13. And you're probably going to notice that I'm doing the odd ones that go with the even ones that you have. Okay. Let me help you out there a little bit so you can you want to write these down. You can go back and look at these to help you with the ones you're going to do. Alright, this is 3 to the 1 minus x equals 1 over 27. Now this one's a little tricky. If you figure out one little thing, then you'll have it. So the base here we could do would be 3. So we can write 27 though as 3 to the 3rd, right? But the thing is, that's not 27, it's 1 over 27. 3 to the negative 3rd. Right? What the 1/3 would be like a cube root. Okay? So, right, we can write this as 3 to the negative 3rd power. And so now, if my bases are the same, then my exponent should be equal. Alright, let's just solve that real quick. Subtract 1, that's going to give me negative 4, so x will be 4. Alright, so you see what you're going to do when you have a fraction like that? When you have a fraction, what's just really going to happen to the exponent? It's going to be a negative exponent. Okay? Alright, so we get 17. Let's see if you can figure this way. You got 4 to the x is 1 over the square root of 2. Okay. So what I'm thinking about on this one is a base of 2. So the left side's pretty easy. 4 is just 2 squared. So let's say 2 squared to the x power. Now, the other side here is what's going to challenge. Now you might do that. There's not really deep in between. Alright. Alright, how can you write 1 over square root of 2 as a base of 2? Negative 1/2. Very good. Did y'all really figure that out? 2 to the negative 1/2. Alright, now, I would think that would be kind of difficult to figure out. Alright, let's think about it. Okay? The square root of 2, we could think of that as 2 to the 1/2, right? Okay? Now, so where did the negative come from? Well, it was in the, right, it was a fraction. It was in the denominator. Okay? Now, so talk to me, does that make sense there?
So it's all square is on top of the negative?
No. Alright? So, let's look at that. It's a good thought. So if you say like this, what if we have this? Same thing. So this would just be 2 to the 1/2. Okay, put it in that column. Alright, so now since my bases are the same, then the exponent should be equal. Now, what do I do here with a power to a power? We're going to see this on our next example, please. Multiply. So it'll be 2 times x or 2x. Now what are we doing here? We're just, the 2's are going away because they're the base, right? And so all we're doing is we're just setting the exponents equal. So we're going to get 2x equals negative 1/2. So now we just divide by 2. Now that's going to confuse some of you. Negative 1/2 divided by 2. We multiply it by the reciprocal. Okay. So this is like negative 1/2 divided by 2, which would be negative 1/2 times 1/2. So it's going to give me negative 1/4. Now, realistically, you can just take that and throw it in the calculator.
Right.
Okay? Especially with that new operating system, when you put in the fractions. Okay. All right. Let's look at one more easy. Okay. And then we're going to go to ones where we're not going to be able to write both sides with a common base. Okay. Let's look at 19. 8 to the x plus 3 equals 16 to the x minus 4. Now, on this one, we can't really write both sides with the base of 8. That's what I would think that first would be 8. So, all right, but right, you said you could write both sides with a base of 2. Somebody said 4. You can't write 8 with a base of 4. Right, but you could do 2. How could I write 8 with a base of 2? To the third. All right, so it'd be 2 to the third to the x plus 3. Okay, and 16 you could write as 2 to the 4. Alright. 4 squared would be 16. Okay. I don't know. Reagan told me to. He's wrong. 91. Alright. Now, since the bases are the same, then the exponents are equal. So, right now, remember the question I asked y'all on that last example about what you do right here? You take the exponents and you multiply them when you do a power to a power. So, when I multiply 3 times x plus 3, I need to distribute. Okay, so it would be 3x plus 3. It would be 3x plus 9. Right? And over here, this would be 4x minus 4. Okay. Now, when it comes to solving them with a common base, it's probably like the hardest one. Okay. Now, we'll solve it. Add this 4 over. And then that's it. Okay. Now, but notice, it was real convenient that we could write both sides with a common base. And if you look at your directions here, your directions kind of tell you that and give you a hint. And say, solve them by writing both sides with the same base or something like that. Now, so let's pose this question, and this is what we're really getting into today with exponentials. Okay. What if I can't find a common base? What if I can't find a common base? I'm like, oh well, can't do this one. We just miss it. Fail pre-calculus. Not go to college. Become homeless. Okay. All because we couldn't find a common base. Right. Here's the idea. Remember what I said the big picture was in exponential equations. To find unknown exponents, what really helps me do that? Laws. Yeah, calculator's going to be involved. It's calculator. Okay. All right. So the answer to that is logarithms. Okay. All right. If you can use logarithms to do it. Now, the ones that you use would be the common logs. Okay. So you could use. Let me write this way. The common log. Because the common log button is on the calculator. And so the common log, what's the base? 10. Okay? Or you could use natural log. Okay? Now, a lot of times, like especially in college algebra, they prefer that you use natural logs instead when you're in college. And there's a pretty good reason why. Because a lot of times, like in Algebra 2, I taught most of you guys by using common logs, all right? But now I'm going to switch over a little bit. I'm kind of seeing what they're seeing in the college level, that natural logs are better, okay? Now, let's look at an example, okay? So we're going to look at number 23. It's on the back side, okay? So all these that are on the back side, I mean, you'll have like number 24 to do probably. You can't write both sides with a common base. Okay? So, but there's no way to write 10 with a base of 3.91. If it is, I don't know. Okay? So this is where we need logarithms. Now, one of the things before we start using the natural log or logarithm, first thing you have to take care of, it wouldn't apply in this one, but you have to isolate the base first. So when I say the base, what's the base in this problem? 10. Okay? So I've got to make sure that base is by itself. Now it is. So if I was like multiplying it by something, I would have to divide it. Okay. What if I was adding something to it, then I would have to subtract it. So I have to get it by itself. Now, after that, then you're going to use, you're basically going to do this. You're going to take the natural log on both sides. Okay. And there again, you don't have to use natural log. You can use a common log. But in college, they like to use natural log. So we'll take a natural log on both sides. And see, this is legal because what I do to one side, I'm doing to the other side. Okay? Now keep in mind what I'm trying to do is I'm trying to figure out what is that exponent right there. Okay? So what's something kind of clever I can do with that exponent so that it won't be an exponent anymore? Right, put it in the front. Okay? The power property. So we have to say x times the natural log of 10 equals the natural log of 3.91. Okay? Now that x is not an exponent anymore, how can I like solve for it now? Right, divide. This x times the natural log of 10. So to undo it, we would just divide by the natural log of 10. And here's where my calculator is going to come in. Okay, so that'll go away right there. And now I'm going to do this because I'm going to round. I think in your directions you're going to say go to 2 decimal places. So you just punch in natural log of 3.1 divided by natural log of 10. Y'all see where your natural log button is?
Oh, yeah.
Yeah, right under the log button. Pretty convenient. Now, so I think you come out with like 0.59. If you don't come up with that, what you calculate? Yeah. So when it opens up the parenthesis in the calculator like that, you have to be sure to close it. Okay. All right. How do we do that? Just punch in natural log 3.91 close parenthesis and divided by natural log of 10. Close that. Now, there again, what you could have done instead of taking a natural log on both sides, you could take a common log of both sides. You did it that way too. Okay? You're going to get the same answer. Now, the reason why you want to do natural logs, used to, I didn't really use natural logs like this, but I kind of bought into it because of this reason, right? If I take the natural log of, say, e to the 4th, so now I'm making my base e, right? So that's the base of a natural log. The natural log of e to the 4th, y'all remember this like from algebra 2, it's just a simple thing, it's just what? I guess you don't remember.
What did you add?
Ricky Bobby. Natural log of e to the 4th is just 4. As we said, the natural log of e to the Ricky Bobby is just Ricky Bobby. Now, look how this works, okay? Now, there again, natural log is a logarithm, but what's the base of it? E. Okay, so natural log and a logarithm of base e is the same thing. Alright, so if I have a log of base e of e to the 4th, you remember how we evaluate this? We say what this raised to what power equals this. E raised to what power would be e to the fourth? Well, e to the fourth. Okay, so that's how that works. Now, that's why we want to use natural logs, because you have that nice shortcut there. Now, let's look at one here where we have a base of e. Okay, so it's actually going to be a little bit of a shorter problem. All right, this one's number 29. And this one's got 5 times e to the x equals 23. Okay, so we can't use a common base, so we need a logarithm. We're going to use a natural log. Now, before we take natural log on both sides, though, we need to do something in this one. You have to get rid of the 5. Okay? So this is the base right here. And so we say we have to isolate the base, so that means we need to get rid of the 5. Right? Yeah, divide it off. Yeah, e to the x equals whatever 23 divided by 5 is. That will be 4.6. Is that right?
Yes.
4.6. Now we're going to take a natural log on both sides. Okay? Now, write it down and I'll say it. Instead of taking that x and like bring it into the front, there's a shortcut. What's the natural log of e to the x? X. Okay? Alright, same idea as right here. Okay? So the natural log of e to the fourth is just 4. Okay. So that's why we use natural logs on all these problems, because of this shortcut. So natural log of 4.6, you can throw it in the calculator. Right. The estimates, so we're going to use the groovy equal sign. 1.5. Alright, let's look at another one with a base of e. Alright, we'll look at 35. Got e to the 5x minus 3 minus 2, 10,476. What you got to calculate? Big one. Alright, right. So you got to isolate the base first. So you got to add the 2. You get e to the 5x minus 3 equals 10,478. You got to add them. Who said 4? Hear me. Alright. Now, so from here we take the natural log on both sides. Now, one person asked, like in second period, how come we wouldn't like add 3 of them? Like, yeah, it's an exponent. Okay. Not like a minus 10, it's a minus 3 in the end. So now, let's take the natural log on both sides. Now, natural log of e to the 5x minus 3 equals natural log of 10,478. Okay, so the natural log of e to the 5x minus 3 is just 5x minus 3.
Do I have to show the middle step?
No, you don't. Okay. And now, the natural log of 10,478. Yeah, about 9.26. Now, all right, now right, you're going to add 3. But now when we do this, when we add 3, we're not going to add 3 to 9.26. Right, you're going to add 3 to what's in your calculator, because what's in your calculator with all those decimal places is exact, isn't it? This is not exact. That's been rounded. Okay? So you say, what's in your calculator plus 3. Okay?
Why would you take the natural log before you got?
You wouldn't have to. Okay? So, right, and then divide by 5. Yeah. So it's like you're just doing one big calculation at the end instead of a bunch of little ones. All right. So, excuse me, 5x is about. Yes. but it's about 12.26, but it's really 12.26 something else, right? Okay. So when we divide by 5 on both sides, again, we're dividing what's in our calculator by 5. It'd be 2.45. So sometimes what you have to do with a lot of these problems is just say you have to use the answer function. You know how to use the answer function?
Yeah, second answer.
Yeah, second answer, and it recalls whatever the last number was on the calculator. Yes.
Is it possible to work an example like that before?
We can. Maybe. Let me get through 37, and then I can go back and do that. Okay. All right. We okay now with this one? Let's look at 37. Okay, this one's got 7 to the x plus 2 equals 14. Okay, now this one, was that base already isolated? Okay, so we're just going to take natural log on both sides. Get natural log of 7. Now a lot of us are going to skip a step right here. Or, hang on, let me, right, it's not equal. Right? So the natural log of 7 to the x plus 2 is not x plus 2. Because that's a base of 7 and not e. So this is when I have to use the power problem. So we write x plus 2 times natural log of 7 with natural log of 14. So in this one, it's a little bit longer. Okay. Because you don't have a base of e. You can't take that shortcut. So now, what am I doing here to solve it? This is what I'm trying to solve for. Right. Because this is multiplying this, right? So the opposite would be to divide. Now, I don't know what that is, because I didn't get that far. The natural log of 410 divided by the natural log of 7. 3.09. Alright, subtract 2, so that would be 1.09.
Oh, these, you don't have to check everything, right?
No.
Okay.
Now, tomorrow we'll talk about logarithmic equations. We'll have to check something on those. But no, exponential equations, as far as I know, I don't think you run into any problems with extraneous solutions. And even in the logarithmic ones, the directions are going to prompt you.
Okay.
Check. Now, all right, which one did you say you wanted me to do for you?
An example like number 4.
All right, so is 39 kind of like that? I don't have it in front of me.
No.
No? All right, hang on. All right, let's make up one. This is going to be on the 6 weeks test because I want to give you a separate test on it, but there's not enough time.
No. Okay. You still have it where our secret
Yes.
is dropping.
All right, now listen to this one. So is that kind of like what you were talking about?
Yeah.
Kind of like number 40 there? All right, so the base is isolated, so we go ahead and take a natural log on both sides. So when I take the natural log, that x over 5 is going to slide to the front, isn't it? We just go ahead and skip that step.
Yeah. Then divide off 2.
Yeah, right, divide by natural log of 2. Go away. Now natural log of 0.8 divided by natural log of 2. I don't know what that is.
Negative
What?
negative 0.32.
All right. You probably, that round is
And we multiply by 5.
right. So you have x over 5 equals that. So dividing by 5, the opposite would be 2. Multiply by 5. So it's not really going to be negative 0.32 times 5. It's what's in your calculator times 5. Answer times 5. Okay.
1.
All right. Now, let me bring something up here that's in the directions that might throw you off. And I'm not going to make you do this part. All right. All right. It says this part. It says express the solution set in terms of natural logs. I'm not going to make you do that. Okay. What they're saying is, like, instead of dividing it out on the calculator, you would just leave the answer in terms of natural logs. Like 24, you would leave as natural log of 8.07 divided by the natural log of 10. That's what the solution would be in terms of natural logs. So you don't have to do that. All I want you to do is go ahead and use your calculator and round it to 2 decimals. So you don't have to worry about this part right here. Okay, scratch it. Yeah.